what instructions come under this category? In this category, the instructions which perform the arithmetic operations, they are included. Arithmetic operations like addition, subtraction, increment and decrement. The first instruction under this category is ADD, addition. The operand of this instruction can be a register or it can be a memory. So this instruction is add register So this instruction add, it is adding the contents of the operand. Operand can be a register. If R is there, then it will be a register, and if M is there, then it will be a memory. So the contents of either the register or the memory, they are added to the contents of the accumulator. So one of the operand will be in the accumulator and another operand will be the register or a memory. Now if the operand is memory, then the location of that memory is specified by the contents of the HL registers. How we are getting the location of the memory? The HL register pair will indicate the location of the memory. Suppose we have here 8040. So at this memory location, the second data will be stored. Suppose at 8040 we have 2. So this 2 and accumulator is having 3. So 3 and 2, they are added up and the result of the operation will be stored in the accumulator itself. So accumulator will have 6 here. Okay. Now if we have a register here, so in that register like B register, C register, D, E, H, L, any of the registers can be used and that register will be added up with the accumulator. If it is a register, then B, C, D, E, H, L, any of the registers can be used and their content will be added up with the accumulator. Now all the flags are modified to reflect the result of the addition. In the 8085 we have 5 types of flags: sign flag, zero flag, parity flag, auxiliary carry flag and carry flag. So while performing this operation, addition operation, if the result obtained after the addition, if the result is 0, then 0 flag will be set. If a carry is generated in adding up the two numbers, then carry flag will be set to 1, and if auxiliary carry is generated, then auxiliary carry flag is set to 1. If the result is having even numbers of 1, then parity flag is set, otherwise it is reset. And if the result is 0, coming out to be 0, or it is a negative number, then sign flag and 0 flags are modified. So all the flags, they are modified to reflect the result of the addition. All the 5 flags will be changed. So this was the add R or either M instruction. Next instruction we have ADC, R and M. This is add register to accumulator with carry. So this instruction is ADC, R or M. The operand can either be a register or it can be a memory location. So this is adding the register to the accumulator with carry. Carry flag is used. So we have this C here. The contents of the operand, either register or memory, and the carry flag, they are added to the contents of the accumulator, and the result of the addition is stored in the accumulator itself. Here also all the flags are modified, and if the operand it is a memory, then the location of that memory will be specified by the HL register pair. Let's take an example. Suppose we have ADC B, that is adding the register B with the accumulator and the carry flag also. Suppose in accumulator we have the number 2 and in the B register we have the number 3, and in carry flag, suppose carry flag is set to 1. So this instruction ADC, it is going to add the B register with the accumulator register and also the carry flag, and the result will be stored in the accumulator. So 2 plus 3 plus 1, it will be 7. So accumulator will have 7 here. Now suppose if carry flag is equal to 0, it is the set condition if it is 1, and reset condition if its value is 0. So if it is 0, then 0 plus 3 plus 2, so the content of accumulator will be 6. So this is how the carry flag and the register, they are added up and the accumulator, and result is stored in the accumulator itself. Now if we are having a memory address, suppose we are having ADCM. So M is the address in the HL register pair. HL will have 8050, suppose. So 8050 memory location, it is having the number 7, and we have the accumulator has 2 and carry flag has 1. So 7 plus 2 plus 1, it will be 10. So accumulator contents will be 10. Suppose if it is 0, then 7 plus 2 plus 0, so the accumulator content will be 9. So this is how this instruction works. It adds the carry flag and the register and accumulator, or it can add a memory location plus the carry and the accumulator. Now the next instruction is ADI. This instruction is add immediate to accumulator. So in this instruction, the operand is an 8-bit data. The operand is defined in the instruction itself. So this instruction is going to add this 8-bit data with the accumulator, and the result of the addition will be stored in the accumulator itself. So this instruction adds the 8-bit data to the contents of the accumulator, and the result is stored in the accumulator itself. And all the flags are modified in this instruction. Let's take an example. We have ADI and 45. So this is an 8-bit data, 45. This will be added with the accumulator. Suppose accumulator has here 5. So this 5 and 45, they are going to add up, and the result will be stored in the accumulator itself. So it will be 50. So in this way, this instruction works, that it adds the immediate data given in the instruction itself to the accumulator, and the result is stored in the accumulator itself. Now next instruction is ACI. This instruction is add the immediate data which is given in the instruction along with the carry to the accumulator. So this instruction, it is adding this 8-bit data along with the carry flag to the contents of the accumulator, and the result is stored in the accumulator itself. Let's take an example. If we have ACI, again 45, then this 45 number will be added to the accumulator. Accumulator is having 5, and carry flag is suppose set. So it is equal to 1. So 45 plus 5 plus 1. So the accumulator will get the result 51. If it is having 0, then the accumulator will have the result 50. So this instruction ACI, it is adding the immediate data which is in the instruction to the contents of the accumulator and the carry flag. All three are added up, and the result is stored in the accumulator. Flags are also modified. If suppose after the addition any carry is generated, then carry flag is again modified, and if the result is 0, then 0 flag is set. Sign, parity, auxiliary carry, all the 5 flags, they are modified during this instruction. The next instruction is ACI. This instruction is to add the accumulator with the immediate data plus the carry. So this instruction is adding this immediate data which is given in the instruction itself to the accumulator along with the carry. So this 8-bit data, which is the operand and the carry flag, they are added to the contents of the accumulator, and the result of this arithmetic operation, it is stored in the accumulator. Now we know that whenever any arithmetic and logical operation is performed, the flags like sign flag, zero flag, parity, auxiliary carry and carry, all these flags are modified so as to reflect the result of the addition. If the number obtained after the addition, it is a negative number or it is a positive number, then sign flag will be modified. If the result is zero, then zero flag will be modified. If any carry is generated, then carry and auxiliary carry, they are modified. And if the resultant number, it is having even number of ones or odd number of ones, then parity flag is modified. So all the flags are modified due to this instruction to reflect the result of the addition. Now if we take an example of this instruction, then ACI and an 8-bit data, suppose we have 45. So this instruction can be written in the program to execute this instruction. Now what it will do, suppose in the accumulator we have 0, 4 and this 8-bit data is 45, and suppose the carry flag is reset, it is in the reset condition, that is its value is 0, then 4 plus 0 plus 45, all these three will be added and the result will be stored in the accumulator. So in the accumulator we will get 4 and 45, it will be 49. If it is 1, then 4 plus 1 plus 45, then the accumulator will have 50. Okay. So this is how the carry flag and the immediate data and accumulator, they are added up. Now next instruction is DAD. Now in 8085 there is an exception that no registers, the contents of the register pairs, they cannot be added. If you want to add any of the register, then you have to add with it to the accumulator. Like we have B, C, D, E, H, L. So no two registers pair, they can be added. If you have to add the contents of any of the register, then you have to move the contents of the other register into the accumulator. So we can say that addition can only be performed if one of the operand it is stored in the accumulator. No two other registers, they can be added. But in 8085 this instruction DAD, it is an exception. This instruction add two register pairs. Okay. So this instruction is about add the register pair to H and L registers. So because B, C, D, E, H, L, they cannot be added up, and if you want to add, then one of the operands should be stored in the accumulator. So this instruction is an exception. It is adding the contents of the register pair either BC or either DE with HL. Okay, so one of the operand will be in the BC registers or DE register, and one of the operand will be in the HL register. So earlier instructions, whatever we have studied about the addition of two contents or two numbers, then their addition was about 8-bit addition. Like 8-bit data will be added to another 8-bit data, and the result is also an 8-bit data. Now using this instruction DAD, we can add a 16-bit number and this 16-bit number, it is stored in the register pair, any of the register pair BC or either DE, and another operand will be stored in the HL register. So both the numbers, they will be added up and the result will be stored in the HL register. Let's take an example. We will write dad H. So what it is doing, it is adding the contents of the HL register pair with the HL register pair. Okay, so suppose in HL register pair, if we have 0, 2 and 0, 3, this is the content of HL register pair, then this will be added, because here we have written dad H, yani HL will be added with HL only. So here also we will write 0203. Both will be added up and the result of the addition will be 0204. It will be 0204 and here we will have 6. Now this addition, it was a 8-bit addition also. You can say that H and H, these are 8-bit data and the result is also 8-bit. You can have 16-bit data also here and then the result will be the 16-bit content. So this instruction, it is allowing the 16-bit addition of the data. Now here we can also have, suppose we have dad B, then the HL register pair will be added with the BC register pair, L will be added with C and H will be added with B. Higher order registers will be added and lower order registers will be added, and accordingly if the carry is generated, then the carry flag will be modified, and the result of the addition, it is stored in the HL register pair only. So the contents of the source register pair, they are not altered. If in this case like that B, if we have in BC register we have a 16-bit data, then this register and HL register pair, they are added and the result is stored in HL. But the contents of the BC register, they are not changed. So the contents of the source register pair, they are not altered, and if the result which we are getting after this 16-bit addition, if it is greater than 16 bits, that is it means carry is generated, then this carry flag is set and no other flags, they are modified. So this was the DAD instruction. Next instruction we have is SUB R and N. This instruction is for the subtraction. It subtracts the contents of the accumulator from the register or the memory. So here we can have the operand as a register also and as a memory location also. So what this instruction SUB is doing, it is to subtract. So subtracting the register or memory from the accumulator. So this instruction is to the contents of the operand, if the operand is memory or it can be a register, they are subtracted from the accumulator. So for subtraction, the subtraction is always done like from smaller number is subtracted from the larger number. Now here we are subtracting the contents of the memory or the register from the accumulator. Suppose in accumulator we have the number 3, and in the register, suppose we are having the register B here, and in this register we are having the number 0, 1. Then 1 will be subtracted from 3 and the result will be stored in the accumulator itself. So accumulator will now have the number 0, 2. Now this subtraction, it is a binary subtraction here, decimal subtraction you have to perform. So if the accumulator, in this case accumulator was having a larger number, so easily the subtraction can be performed. Now if the accumulator, it is having a lesser number, suppose 1 is in the accumulator and 3 is in the register, then you have to subtract the 3 from 1. So now you will get a negative number, and this negative number will modify the flags. In the sign flag, it will be set, that means its value will be 1 if the result of the subtraction is a negative number. And if some carry is generated, means borrow is generated, you have to borrow here, then carry flag and all these flags are also modified due to this instruction. Now if the operand, it is a memory, then the address of this memory location, it is specified in the HL register pair. Suppose we have written here sub M, then the address of this memory location will be given by the HL register pair. Suppose we have 8050 here, then our second number will be stored at this memory location. Suppose we have 1 here, then this 1 will be subtracted from accumulator and result will be stored in the accumulator itself. So this is how this instruction will be executed. It subtracts the contents of the operand from the accumulator, and also all the flags, they are modified to reflect the result of this subtraction. Next instruction we have is SBB. Now in case of addition we were having carry. Now in case of subtraction we will have borrow. So this instruction is doing what? It is subtracting the source. Source is our operand. It can be either a register or it can be a memory location. It is subtracting the source and the borrow from the accumulator. So this instruction, what it is doing, the contents of the operand can be either the register or it can be a memory location. It can be a memory. And the borrow flag, they are subtracted from the contents of the accumulator. Now if the operand it is a memory, then its address is given by the HL register pair and all the flags are modified. Just the difference is there that in the SUB instruction we are subtracting the contents of the register and memory from the accumulator, but in this SBB instruction we are having this borrow flag also. So this borrow flag is also considered and it is also subtracted from the accumulator. Now example, we can write here SBB. We can write any of the registers we can use, like SBBC register we have used, or we can write SBBM. If it is M, then its address is given by the HL register pair. Suppose in HL we have 2034, then one of the operand will be in the accumulator, and we have the borrow flag. We have to consider the borrow flag also if it is 0 or 1, and the second operand is stored at this memory location 2034. So this is how this instructions execute. Now next instruction we have is, it is again for the subtraction. Now this instruction is SUI. This I means we have an immediate data here. And this immediate data, it is given in the instruction itself. So what this instruction does, it subtracts the this 8-bit data from the accumulator. So this is subtracting the immediate data with the accumulator. No borrow flag. You don't have to consider borrow flag in this. Only this data and the accumulator. So this instruction, it is subtracting the 8-bit data from the contents of the accumulator. Result is stored in the accumulator, and all the flags are modified due to the execution of this instruction. Now example, we have SUI and 45. So this number 45, it will be subtracted from the accumulator. Suppose in accumulator we have 50. Then 45 will be subtracted from 50, and the result will be stored in accumulator, which is 0, 5. And if there is any borrow, suppose in this number we have is 45. Suppose we are having here 55. Then we will subtract this 55 from 50. Then we have to take a borrow. Then the flags will be modified to reflect the result that a borrow has been taken to perform this subtraction. So this was SUI, that is subtracting the immediate data from the accumulator. Next we have SBI 8 with data. Now this instruction, it considers the borrow, because here B is for the borrow and I is for the immediate data and S is for the subtraction. So this is doing the subtracting the immediate from accumulator with borrow. So this instruction, it is subtracting the 8-bit data along with the borrow flag from the contents of the accumulator, and the result is stored in the accumulator itself, and also all the flags are modified to reflect the result of the. These were the subtraction and the addition instructions. You can notice that in all the addition and subtraction instructions, we have used the one of the our contents will be in the accumulator. We have add, ADI, ADC and ACI. These are for the addition. And for subtraction we have SUB, then SUI, then we have SBI and we have SBB. So these four were for the addition and these were for the subtraction. We were having two operands, two numbers we require, and one of the number is in accumulator and the second number, it is in the, either it is stored in the register or it is stored at a memory location. And also we can have an 8-bit data directly given in the instruction itself, that is immediate data. And one instruction was our exception, that is the DAD instruction, which is adding two register pairs. It is adding a register pair with the HL register pair. So these were for the addition and subtraction. Now next instructions which come under the category of arithmetic operations or arithmetic instructions arithmetic instructions are increment and decrement. Increment is increasing the number by 1 and decrement means decreasing the number by 1. So first we will study the increment instruction. So we have INR, R and M. So this instruction is to increment register or memory by 1. So this register, it can be any of the registers A, B, C, we have D, E, H, N, L. So any of the register, it can be incremented by 1 or it can be a memory also. Now this memory, address of this memory location will be given by the HL register pair. So this instruction INR, it is increasing the content of the register or the memory by 1. And the result is stored in the same place. Suppose take an example, we have INR B. So in the B register, a number is stored, suppose it is 3. So this INR B, it will increment the instruction, this register by 1. So the content of B will now become 0, 4. So the result of this increment instruction, it is stored in the same place. If we have written INR C, so in the C register, if we have 4, then this will be incremented and it will become 5. It will be incremented by 1. Just remember that here only the register is incremented by 1. We are not taking the register pair here, only the register. It can be any of the register, it can be accumulator, B, C, D, E, H, L, any of these registers, and they can be incremented by 1. Now if the operand it is a memory, then the address of this memory location will be given by the HL register pair. So this was INR. Again, we have a modification of this instruction. We have INX R. Now this instruction is used to increment the register pair by 1. So here register pair is incremented by 1. We can have the registers pair as BC, we can have DE, and we can have HL. So any of these registers pairs can be incremented by 1 using this INX instruction. Now result of this increment will be stored in the same place. Let's take an example. If we have BC register, we have 8050. Then it will be plus 1 incremented by 1, and the result will be BC will have 8051, because we will add this 1 in the lower order register. C is the lower order register, so plus 1 will make it 51 and 80 will remain as it is. So this complete register pair is incremented by 1. So this INX instruction we can use to increment the register pair, and result is stored at the same place. Similarly, we can have INX, this was INX B, then we can have INX D also, and we can have INX H also. So through this the BC register pair will be incremented, through this DE will be incremented, and through this HL will be incremented. So here register pairs are incremented by 1. Now these were for the increment, and then we can have the same instructions. Just difference of this will be that now we will have decrementing the register or the register pair by 1. So just we were having INR for incremented, INR R and M. Here we have DCR R and M for decrementing the register or memory by 1. So the contents of the register can be B, C, accumulator can also be there, D, E, H, L, any of the register, it can be decremented by 1. And if it is a memory, then the address of this memory location, it is specified in HL register pair. The result of this instruction, it is stored in the same place. Suppose we have we have DCR and C, and in C register we are having 5. So this will be decremented by 1 and the new contents will be 0, 4. So the content will remain stored at this, the result is stored in the same place. It is not stored in the accumulator. It is stored at the same place and the number is decremented by 1. Similarly, we can have DCR M, and M, this address will be specified in HL register pair. We have suppose 2034, then at 2034 if we have a number 6, then it will be decremented by 1, and now the new data will be 0, 5. So this is how this instruction DCR works. Now next instruction we have is DCX. This instruction, it decrements the register pair by 1. Just like INX was for incrementing the register pair by 1, DCX is for decrementing the register pair by 1. So the contents of the register pair will be decremented like BC, DE and HL. Any of the register pair, it can be decremented by 1 and the result is stored at the same place. Now in DE, suppose we are having 2034, then it will be decremented by 1. So the new contents of the DE register pair will be 2033. And we can have the instruction for this DCX D. We can have DCX B also. We can have DCX H also. So this is decrementing the register pairs by 1. Okay. So these were the increment and the decrement instructions. INR, INX, we were having INR, INX for the increment, and we have DCR and DCX for the decrement. Now next instruction we have is DAA. This is decimal adjust accumulator. D is for decimal, A is for adjust, and this A is for the accumulator. This instruction is used in the BCD operations. When the microprocessor it is performing the BCD addition, then this instruction is used. So this instruction it is used when the microprocessor it is performing BCD operations. BCD means binary coded decimal. Now in the microprocessor we have all the numbers in the decimal notation, that is in the form of 0 and 1s. So this instruction decimal adjust accumulator, it changed the contents of the accumulator which are given in the binary value to two 4-bit BCD digits, because accumulator it is an 8-bit register. So we were having 8-bit data. Now this 8-bit data which is given in the accumulator, it is changed into two 4-bit datas. This is 4-bit and 4-bit, which is in the BCD notation, because this 8-bit data it is in the decimal notation, so it will be converted into the BCD notation and it will get converted into two 4-bit datas. Now this is the only instruction which is using the auxiliary carry flag to perform this BCD conversion. So it can be asked that which instruction uses the auxiliary carry flag. So this is the answer, that the decimal adjust accumulator instruction, it uses the auxiliary carry flag to perform the BCD conversion. All the other flags, they are also modified to reflect the result of the addition. Now how this BCD conversion is performed, let's see. This is our 8-bit data, and the lower order 4 bits, they are greater than 9, or if the auxiliary carry is set. So if this auxiliary carry flag it is set, that means its value is 1, then this instruction it adds 6 to the lower order 4 bits. So this 6 will be added to the lower order 4 bits, and we can have the 4 bits which are in the BCD notation. Now if the value, this was for the lower order 4 bits. Now if we have the value of the higher order 4 bits, it is greater than 9, or if this auxiliary carry flag it is set, that means it is 1, then the then this instruction it adds 6 to the higher order bits. So if higher order bits are greater than 9, then the instruction it adds, and if this carry flag it is set, then this 6 is added to the higher order bits, and the result we have is the 4 bits in the BCD notation. So this is how the BCD conversion is performed, how a decimal number is converted into the BCD notation. If lower order bits they are greater than 9, then add 6 to the lower order bits, and if the higher order bits they are greater than 9 and carry flag is set, then add 6 to the higher order bits. To perform this BCD conversion in the microprocessor, we will just write DAA. This instruction it is having implicit addressing mode. Implicit addressing because the operand it is given in the instruction itself. Operand is the data, or it is something on which we are performing the operation. So we are here performing the operation on the accumulator, and accumulator it is specified in the instruction itself. We need not to specify it externally, it is implicit in the instruction. So this type of addressing is implicit addressing. So this instruction DAA it is an example of implicit addressing mode. So this was all about the arithmetic instructions. The arithmetic instructions they involved the operations like addition, subtraction, increment, decrement, and the last instruction we studied was the decimal adjust accumulator, that is the BCD conversion. So these instructions were they fall in the category of arithmetic instructions. Next we will study the branching instruction.